Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks. Hello and welcome to IEEE Soft Robotics podcast. Hello, Professor Douglas. Thanks so much for joining us on the podcast. Such an honor to have you.
It's a pleasure to be here. Thanks for having me.
Thank you. So I'd like to ask you first, how would you like to define yourself for the audience who may be first time listening to you?
Sure. So I'm had a bit of a strange academic journey. I started as a chemist and then did polymer science, material science, and then did some work in fluid mechanics. I think I would define myself as a mechanician, theoretical and applied mechanics. And I think I'm probably somewhere between a mechanician and a soft matter physicist. So I kind of look at problems that involve mechanics of objects that we see around us.
I'm curious also about your childhood, about the childhood. How was your childhood in terms of being interested in science or tech in general?
Yeah, sure. I was curious about science from a young age. I definitely was reading the Magic School Bus books and encountering all sorts of different problems, from being really into computers at a young age and just kind of really interested in how things work. And so I think that's kind of where I got my start. I think just kind of curiosity from a young age.
Great. So first of all, congratulations for your new paper, for you and the team. But I guess let's speak first about how do you see definition of soft robotics? Because we have a recent paper about that we shouldn't have all time to design soft for the sake of being soft. That's paper hard problem for soft robots. And we have discussion also podcast about that. But I'm curious about what do you think about soft robotics when it comes to, how do you see it? Or, a definition maybe.
Sure. I fully and firmly agree with the statement you just made about, kind of trying to resist the urge to make things soft just for the sake of being soft. And I'm always kind of making these comments when talking with roboticists about, the things that we think of as soft, maybe having a hard exo or endoskeleton or having some stiff components or I think the biggest thing I think about when I think about soft robotics from the perspective of a mechanician who has also studied material science, I tend to think, or at least I want to remind people, that soft doesn't have to mean material squishiness. Soft can mean compliance, and compliance just means the ability for something to deform. And that softness can come from geometry and a structural form rather than materials. And we see this all around us. You take a sheet of paper, which has a really high elastic modulus. It's hard to stretch a sheet of paper. But at the same time, it's really floppy. It's really bendy. It's easy to crumple a sheet of paper into a ball. And so to me, that's softness as well, is to have something that's really easy to bend or rotate or twist or deform. And so when I think about soft robotics, I kind of want to infuse the idea that it doesn't have to be PDMS squishiness. It can be softness coming from compliance, softness coming from structures, softness coming from geometry. And the paper we just published on these soft robotic grippers, I mean, they're not that soft. They're Mylar. It's a 3 gigapascal elastic modulus. It's not a soft material. But if you make it thin enough, it's really flexible and it can bend in really extreme ways. And so I think when I think about kind of softness in the context of soft robotics, I often am trying to remind people to think about kind of softness broadly defined.
That's really interesting, but I guess I'll ask you, do you think in that case, why do you think we don't, for example, exploit this kind of compliance when it comes to geometry? It's not material science. So why do you think that's kind of, I don't know, how do you see the community understanding this kind of aspect of geometry and morphology and how we can play with geometry to make it compliant, even if we have very young models, the example you mentioned?
That's a good question. I think there's a couple reasons. I think for one of these reasons is, for a long time there was kind of a bit of a divide in terms of what people in material science were studying versus what people in theoretical and applied mechanics were studying. And I think because of that, there wasn't a ton of people trying to sit at that interface. That probably started changing like 15 or 20 years ago, at least at the APS, American Physical Society, annual meeting. There started these smaller sessions on what were termed extreme mechanics. And so looking at mechanics, instead of just thinking about small strains and big steel I-beams, thinking about mechanics of paper, thinking about the mechanics of your skin, thinking about the mechanics of the stuff that's around you. And I think at that point, that's when you started seeing people from the material science world blending a bit with people from the mechanics world, and looking at certain problems that could be solved either by changing materials or could be solved by changing geometry. And so I think that's one of the reasons why it has kind of taken a while to think about that. If you're a material scientist, you think about the material that you're using. Should we change the material? Should we functionalize this material in some way to make it do what I want it to do? If you're a mechanician, you're honestly oftentimes thinking, I want to use the simplest material I possibly can, you put it into the simplest shape I can, and see if I can predict how that structure is going to deform. And so part of what I think has happened in the last maybe 10 years is that you've seen all sorts of rapid prototyping tools emerge that made it easier for mechanics people to play with different shapes and create things with laser cutters and 3D printers, and study the structures. And at the same time, those same tools allowed people from a material science background to be asking similar questions.
Yeah. So I guess to skew in that case, because I think that's a question we can ask, how we can extract this beneficial geometric, either nonlinear geometry structure design, and also couple it with the material properties, for example, material nonlinearities. And do you believe material nonlinearities or the material characteristic is more dominant when it comes to geometric, the design of geometry, whatever you select to get certain functionality? How do you see the coupling between both of them, and which one we can see is more significant to get your functionality?
Yeah, that's a good question. And the challenge with answering it is it's probably really dependent on the particular problem you're trying to solve. And so, I think one of the things that you're seeing emerge in the mechanics community is being more open in discussing kind of what effect does changing geometry have relative to changing materials. And so one thing where you can really easily see the dramatic difference between geometry and materials is with slender structures. So things that are thin in one direction, rods, plates, shells. These are structural components that are everywhere around you. These are thin in one dimension, and you can pretty quickly, with like a back of the envelope calculation, show that the energetic cost to stretch a thin material, it goes up with the elastic modulus and it goes up with the thickness. But the energetic cost to bend a material goes up with the elastic modulus and it goes up with the thickness cubed. And so there you see a huge difference. So thin structures prefer to bend. They don't like to stretch. And the reason is because the bending energy gets really, really small as that thickness gets smaller because you're cubing that value. And so I guess the thing I would say is if you need to make something more bendable, if you cut the elastic modulus in half, you're just going to cut the bending energy in half. But if you cut the thickness in half, you're going to take that and cube it and get a much more significant effect there. So you can do analysis like that for all sorts of things. If you're trying to make a structure that's going to be twisting, or that is going to be stretching, or there's going to be shearing. And then I think if you can start from, what am I trying to get this thing to do? How am I trying to get this to deform? And then there's usually, with a little bit of effort, you can come up with a back of the envelope calculation to estimate, is it better for me to be changing the material, or is it better for me to be changing the geometry and the structure? And oftentimes some kind of order of magnitude estimates will tell you like, oh, wow, actually, if I just double the thickness or half the thickness, I don't have to change anything. And in terms of the material I'm using, which, I think is like bittersweet if you're a material scientist, right? Because that's your field. You're studying, what novel materials can I make to solve this problem. But at the same time, we also have really well-established fabrication techniques for the materials we use. So it'd be kind of great if we could use the same materials, but just play with their geometry to get the functionality we want.
That's a good point. So I guess let's secure that case. Do you believe what you mentioned, there's unavoidable trade-off that you can't get around? If we speak about, I don't know, from geometric perspective, you mentioned the sickness, the example, if you try to play with that, but I don't know if you use or experiences as something you have witnessed a trade-off here, and you can't really get around it. I don't know if you have any.
Sure, that's a good question. And so, yeah, one of the trade-offs is that, so thin structures are really easy to bend. We use these thin Kirigami sheets to make grippers out of them. But the challenge with thin structures, and this has always been the challenge with thin structures, everyone is trying to design engineering structures that are lighter in weight, thinner, can perform the task, whether it's carrying some load or whether it's the shell of an airplane. We want our objects, we want our cell phones to be as thin as possible and as small as possible. But the trade-off there is that thin structures, even though you kind of can gain some stiffness in some directions, they're really prone to instability. And that's where you have to be really careful. And so that's where you have to be aware of, okay, if I change the geometry of the structure, I might be making my structure susceptible to buckling when I'm not expecting it, or going through a snap through instability where it really is going to catastrophically kind of change shape in a way that you may or may not want. Now, I think what has happened in the mechanics community for the last, again, like around 20 years or so, has been this tendency and this approach to try to see if we can make elastic instabilities functional. And that has been an area where we're saying, okay, if we use materials that are not going to, if you take a soda can and you crumple it, that thing is not going back to a soda can. It's plastically deformed. It is destroyed. But if you use materials like soft rubbers or even some plastics, you can get these large deformations so they can go through a big elastic instability, buckling, snapping, wrinkling, and not be permanently destroyed. They can come back to their original form if you want. And so engineers and mechanics folks have been looking at ways to utilize instabilities in a functional way. And actually, to be honest, at the heart of like the way these Kirigami grippers work, there's a buckling instability that happens. And it is kind of, we are basically using buckling to allow these structures to kind of bend in the way we want. And so that's an example. I mean, we're taking advantage of an elastic instability. And for a long time, engineers, I mean, if you were studying mechanical engineering 20, 30 or 40, 50 years ago, you're typically thinking about instabilities as something to be avoided at all costs. And okay, where's the buckling load? Let's add a factor of safety so that we never get anywhere near when this thing's going to buckle. And now I think you're seeing people saying, wait a minute, we might be able to do something cool if we let this buckle. What can we do with it?
That's a very interesting point. I think that's something you speak about also, the buckling and how we can use this kind of, maybe what you mentioned, available in the community. And I guess to in that case, if we use this kind of behavior or that we try to avoid, do you think it could replace the controller and the way we try to force the robot to behave in a certain behavior, just forcing or resisting this kind of dynamics that come for free, for example, in your example? That's maybe the first question. I'm curious, what do you think about that?
Yeah, I think that's a great idea. I think the link that you're kind of getting at there is, how do we turn an instability into kind of a feature in a mechanism, because that's what we want. We want some mechanism, whether it is, in the case of soft robotics, maybe it's some locomoting motion of your elements, or whether it's kind of some large deformation that might change the angle or the rotation of it as it's deforming. I think if we can kind of use instabilities as a way to design mechanisms, we can kind of use the structure kind of use the nonlinearity, in particular, like the geometric nonlinearity of that structure, as a way to do functional things. So I think of it as kind of like, if you have a mechanism or a motion in mind, can you design that mechanism with instability kind of at the heart of it? And sometimes that's not going to be useful, and sometimes that's not going to be helping your design improve. But I do think that it can be easier to try to incorporate that instability sometimes than it can be to try to circumvent it or avoid it.
That's a good point. So I guess in that case, do you think what kind of material, because you already have the experiences, do you think there's kind of limitation when it comes to selections and material that would give you what you're expecting? For example, instability that you can use later for a favorable system. I don't know, do you think that material selection is limitation when you come to, if you wanted to extract what you're looking for, if there's a limitation here?
That's a good question. I think the materials, if you're playing with, so for my lab's experience is oftentimes with slender structures, so things that are really thin, and in those cases geometry tends to be the kind of the dominant factor in terms of what you see. But as you start to play with different material systems, maybe materials that are bound to a surface or at an interface between two materials, or maybe just bulk 3D materials, I think, we're not here yet, but I think we can get to a point where we can start thinking about a class of geometric nonlinearities that could be functional and used to do interesting things. And then we can also think of a class of material nonlinearities that could be functional. There's not as much work kind of with people combining material and geometric nonlinearities to do really novel things. So utilizing buckling alongside of plasticity, or a snap through instability along with viscoelasticity to get some really interesting, maybe it's dynamical control of your system, or some damping in some systems. I do think there's a lot of opportunity to be thinking of them together, kind of synergistically, to how can we use nonlinearities that are unique to the material system we're using, along with kind of tuning the geometry for that material. It's kind of together do something new. I suspect that's where we'll see kind of advances in the next 10 years. I think the challenge is it's harder. Like nonlinear things are really difficult. And I think what you see in the mechanics community is we work a lot on geometric nonlinearities, and then we assume everything's linear and elastic and simple, and the material is like some magical rubber that doesn't really exist. And that's because it's really hard to model things that are just completely nonlinear in their geometry and their materials. But I think, I think that is where we'll see some really interesting innovation going forward, is kind of coupling those two.
Great, that's an excellent point. But I guess ask you, when, for example, the structure you've tried about, how do you see integration of different materials with different, I don't know, young models or maybe properties? How do you see the integration of different materials so that you can have this kind of, I don't know, the functionality you aspire to have in your system?
Are you talking specifically about these grippers or in general?
In the gripper, and also in general in the field, if you can speak from what you're doing, do you believe that if you combine different materials with different, I don't know, significant different mechanical properties, how do you see it significant to get what you're expecting, if you have any experiment like that?
Yeah,
also with
sure.
in general, when it comes to geometry and integrating each material, what kind of geometry do you think you have to consider to integrate two materials, or more than that?
Yeah, that's a good question. I think that, specifically in the case of, for instance, these grippers that we were working on, if we could design them now, knowing what we know, if we could go and kind of make the next generation of these things, we recognize now what each part of the structure is doing. So for instance, in the grippers that we discuss in this paper, there's a hinge in the center of this gripper that is really responsible for the grasping motion. And we know that the thinner we make that, but really just the easier we make that part to bend, the easier it will be for these grippers to work. So you could either make that easier to bend by playing with thickness or playing with material properties. But then you also have another component of the gripper are these, we call them skew plates because they're like plates, but the edges are skewed. It doesn't matter. But they're basically plates. And these are the things that are really doing the heavy lifting, literally. Like they're the things that are kind of grabbing the object and resisting bending out of the way and dropping the object. And those have completely different kind of design requirements than the hinge does at the center. The plates really want to be stiff. The stiffer those plates are, the harder it is for that object to bend them out of the way and for them for the gripper to drop the object. And so you could think about kind of taking this really simple structure that we just cut out of plastic. And if you wanted to make it better, what you would do is say, okay, we know we need the hinge to be really bendable. We know we need the plates to be really stiff. But then we also have a third component to this gripper, which is these little appendages on the side. And these little appendages are really kind of like the tips of your fingers, which is, you know, they're actually grabbing the object, and they are, depending on the size of them, they're able to grab smaller objects or bigger objects. But then also, here's where structures and geometry really don't help us too much, is we kind of want those appendages of the gripper to be have a really high resistance to sliding. So it's a really frictional material there. We don't want something that is going to be slippery. You want to have some grip on the material. And so if you think of these Kirigami grippers in terms of how do we make them better and how do we keep in mind ideas of geometry and materials, well, the hinge needs to be bendable, the plates need to be stiff, and the appendages need to have a really high coefficient of friction so they can actually kind of pinch some object without something sliding out. And so then you could start tailoring the geometry and the materials for each of these sections independently. And this is where you would need kind of some of the really advanced and up and coming rapid prototyping, 3D printing technologies, so that way you could actually be integrating gradients of materials that give you the functionality you want.
Thank you for saying that. Yeah. And of course, this the question I think the student also hears about how you start the process of the design, because when you start to think about certain geometries, of course, there's some initial guesses that you can do. But when you try to design, how the process goes to start with thinking of certain geometry and model it, and what's the first crucial step you believe that to get to the right design or accurate design, even for simulations, because in the paper, how you do that?
Sure. So our research group's approach to these types of things is we tend to simultaneously just make stuff in lab and see what happens to it as we poke on it, pull on it, twist it, as we change cut lengths and shapes and orientations in different places. And then we try to go back and think about what is the simplest kind of canonical problem that we can study, so we can build up like a foundation of understanding and intuition. And we go back and we play some more, and then we kind of go back and forth. So to give you a more specific example, you know, we started out by playing with really complex cuts and sheets and pulling on them and seeing them do all these crazy things, just really large, messy deformations. And while doing this, we went back and decided, okay, the simplest kind of possible problem that we should study if we're going to look at cuts and sheets is we should just take a sheet and put one cut in it in the center and pull on it and see if we can predict what's going to happen. And we can just vary the length of that cut and just pull on it and see what happens. And so we did this, you know, maybe 3 or 4 years ago now, where we looked at basically two really simple problems. What happens if you put a cut in the center of a sheet, and what happens if you put a cut on the edge of a sheet? And it turns out that you start to see some kind of really qualitatively clear behavior. If you put cuts in the center of a sheet and you pull on it, the center of that sheet's going to pop up. So you get kind of a lift motion. If you put cuts on the edge of a sheet and then you pull on it, the sheet is going to rotate. And so the edges of those sheets are going to rotate. So now we kind of have some building blocks to give us some intuition. We know that cuts in the center of the sheet are going to give you popping up or popping down motions, while cuts on the edge of the sheet are going to give you rotation. And if you look at the design of the Kirigami grippers, you start to see that we make these things where there are center cuts and edge cuts, and the edge cuts are allowing some rotation, and the center cuts are kind of giving you some upward or downward bending deformations. And so our approach has always been kind of to play with the more complex, intricate, and oftentimes, to be honest, useful structures.
Mhm.
But then we kind of go back and we say, we write a lot of papers that are studying really simple shapes and how they deform, spherical shells, poking on them, elastic rods that you poke on or you twist, like I was saying, sheets that you put a single cut in and you pull on them and see what happens. And so we try to do kind of the really cutting edge and fun playing alongside the kind of foundational, like really intricate, simple, like how can we simplify the geometry? How much symmetry can we have as possible? Can we just make this as symmetric as possible so that the math is actually doable? And so we try to go back and forth along with playing and kind of developing some fundamental intuition. That's been our approach, with this problem, but kind of across the board. That's how we tackle problems in my research.
Mm-hmm. So I'm curious about the redundancy, because we speak also about how we can design robots that have kind of redundancy. When it comes to robotics or geometry as well, how do you consider the redundancy? For example, if you mentioned the example, if there's damage happening in, I don't know, in the structure, how you consider the redundancy design?
Yeah, that's to be honest, I haven't thought a ton about this question in terms of adding in kind of redundant behaviors for certain tasks. And part of this is to be completely honest, is just my not being a roboticist, and so I'm not generally kind of building functional robots. And so I would say, from my perspective, on the mechanics side, I think about kind of mitigation of potential failures. And so I think if you're someone who studies mechanics and you're looking at problems that involve cuts in thin sheets, or even if you're not someone that studies mechanics, even if you're just someone that has taken a piece of paper and put a cut in it, and you know that if you pull on that thing, the paper is probably going to tear. Mm-hmm. And so you might be looking at these Kirigami grippers saying like, okay, that's great, but you just put a bunch of cuts in your sheet. Aren't they going to just break after you pull on them for a while? And so we think about, yeah, that's definitely true. That's a concern. You will have kind of plasticity at that crack tip. You will eventually have crack propagation there. How do you mitigate that? And so one of the things we do, these are mechanics, these are the things that we understand a lot about in mechanics. And we know that if we can take that same cut pattern, take those same cuts, and instead of just making a straight line cut, if we can kind of make a barbell shaped cut where we put a little circle at the end of the cut, that circle is a little bit bigger than the width of the cut, then what that does is it reduces the stress at the end of the cut, and it makes it so that there's not too much stress there. It's not going to concentrate. It's not going to tear. So while we haven't thought a lot about kind of redundancy in grasping operations, what we have thought about is mitigating the way we expect things to fail. And in the case of this problem, we expected crack propagation to be something that we should think about. And so we discussed kind of mitigating that. Your viewers at home can't see this, but I'm kind of holding up like an example where we have kind of these dumbbell shapes, and we can play with kind of, okay, how big does that circle need to be and where does it need to be, so that we can at least make the structures that we're making more robust and reliable for large numbers of cycles of use.
Mm-hmm. That's a very good point as well. Yeah, but I could ask you if there's any counterintuitive maybe behavior when you're trying to do the modeling or maybe simulation, but maybe counterintuitive when it comes to what you try to do, behavior, or surprising you didn't expect. I don't know if you have any kind of moment like that.
I primarily study elastic instabilities, and these things kind of continually provide me with counterintuitive behaviors. They kind of are always testing your intuition, because things buckle and snap in unexpected ways all the time. And especially on the modeling side, it can be incredibly easy to set up a finite element model that does not capture buckling instabilities that will happen in real life. And that is among the hardest things to do when studying or developing computational models for elastic instabilities is sometimes instabilities occur when you're not expecting them. And if you don't kind of properly set up your code to be able to capture them, you'll completely miss them. And that can be really that problematic if you're seeing elastic instabilities occurring in real life that your computational model isn't predicting. I can give you one that as a counterexample that we actually haven't we still haven't figured out why this happens yet. But if we take the same if we take the Kirigami gripper that we talk about in the paper and you pull on it, it makes this nice grasping motion. And as you start to, we talk about towards the end of the paper, combining these unit cells together in series, so that way you have a gripper that's able to grasp a long, slender object like a pen. And what's really surprising, an example of a counterintuitive instability, is if you take that kind of Kirigami gripper that's in series and you start to make the cuts closer and closer together, then what happens is, and I'll show this to you. Maybe I can send a video to you. You can post. But what happens is you pull on this object and it starts to curl, and then it completely fails and does something incredibly counterintuitive. So if you make the cuts too close together, it starts to make a grasping motion. And then as you pull just a little bit further, the grasping motion completely goes away. The structure just stretches and it buckles in a way that, to be honest, we still haven't completely quantified. And so, in the paper, we kind of say, make your cuts this far apart. Well, that's because as you make them really closer together, the behavior gets significantly more complicated, and we don't really know why. We have some ideas, but that's an example of, like, we did not expect these sheets to kind of start to curl and then just stretch and kind of snap back to a kind of stretchy spring-like deformation. And so, but in general, this happens all the time when you're playing with slender structures. They're so nonlinear that their deformations can be really hard to predict, and they can often be really hard to kind of intuit. It is a problem that kind of needs to be on the forefront of your mind if you're doing computational modeling, because, as I mentioned earlier, it's very easy to set up a model that'll miss these instabilities.
Mm-hmm. That's very excellent points. Yeah, but do you believe, based on what you mentioned, I don't know what kind of question or hints do you believe that you have to go more and investigate more? Because modeling, you say, sometimes, most of the time, it doesn't really capture what we have experiment. We can't understand how it's happened or come up with models. Sometimes it's happened. For you, would you have any kind of direction, do you believe, for what you mentioned, that you have to investigate more in that direction?
So I think about this a lot in terms of especially this work on Kirigami, because there is a ton of different directions we can go in terms of playing with cut configurations and the materials that we're using and the tasks that we want to perform. And I think, from my perspective, I guess to tie it back to what you're asking in terms of on the modeling side, I want to be at a point where our computational models are kind of a really complementary tool to our experiments, where some experiments are really easy for us to do. So let's go in the lab and do them and see what happens. But some experiments are incredibly hard to do. It's hard to turn off gravity. And so it could be really nice if you can run a computer simulation with your structure and see if gravity is what's causing you trouble in the lab. And so I'm collaborating a lot with computational mechanicians to kind of develop tools to be at a point where we can be playing with them in the same way that we can play in lab. And I think that's something that I think almost more about kind of broadly than I do with the specific directions. Is I want the ability to play on my computer with a model in the same way that I can play in the lab with a structure. And I don't think we're there yet, but I want to I think that to me allows you to really think extremely creatively about the kind of the phase space of your experiments. And so,
yeah.
Yeah.
That's very interesting point. I'm curious to ask you in that case about the simulation, because you use finite element, and we know sometimes in mechanics there's techniques don't depend on the mesh, for example, extend FEM or NBM. There's other techniques. I don't know what you've experienced about the design and the expectation, because you try to look for certain parameters, and sometimes simulation is not really accurate 100% when it comes also to simulating nonlinear material. Or I don't know what you remark about that, if you can say more about what could be done in that area.
I think that's a hard question to answer, because it really depends on the computational mechanics tools people are using and the understanding of the assumptions that are in the models that people are using. And so I tend to think about making sure that we can be aware of where our simulation could go wrong and where our simulation should be accurate, and kind of constantly validating things with comparing what the simulations are saying to what the experiments are saying. I think that there are things that are really challenging for computational mechanics to incorporate. Not impossible, it just takes extra care and thought. I think one of the things that's easy to do in lab is to make contact with various objects. Take a gripper and have it grasp around an object. We don't know exactly where that gripper is touching that object, and that makes the problem really hard to solve computationally, is to actually have something that has moving contact points, and the structure's deforming, and there might be friction at that interface. Those are delicate problems that require kind of a lot of care from the modeler to be taking into account what they can do quickly and easily, and what they can't. And you'll notice, like in the computational models we use in this paper, we're not grasping objects. We're showing how the structure works. We're showing how the Kirigami gripper deforms when a force is applied. And we can validate that and show that it works by comparing the force displacement curves to what force displacement curves we get from our experiments. But it's really hard for us to take that model, put an object that it's going to pick up and grasp in these computational simulations, and test it that way, because those are hard problems. And now, we could have spent a couple of years or a year or so kind of developing computational tools necessary to do that. But I think what you see oftentimes is just a trade-off in terms of, this is what we can do easily, so we did this, and this is what we can do easily, so we did that. And I think then it's again, kind of going back to one of the earlier points that we touched upon. A lot of times it comes down to, what questions are you asking, and making sure that you're asking the right questions to the right tool. And I think that, to me, I think about computational modeling as a tool in the same way I think about experiments as a tool. And they're all tools towards answering questions, and some of them are going to be better suited to answering some questions than others. And I think it's really the job of, especially nowadays with the kind of ease of computer modeling, the ease of rapid prototyping and doing experiments fairly quickly, there's a lot of burden that falls on our shoulders to design good experiments, design good models, and ultimately ask the right questions of these tools. And I think that's a really important and overlooked aspect of it, is how do you know what tool is going to help you answer the question that you're really interested in? Because you could spend a lot of time either forcing a tool to try to answer a question that it's not suited for, or taking a tool and kind of not being aware that you're actually answering a different question than you set out to answer. And I think those are really, that's where the experience of doing research for a while comes in, is just kind of understanding, what am I trying to ask, and how do I get these answers?
I really like this point. It's a very excellent point. And I think that's something sometimes we speak about, what leads sometimes, we're not speaking that something happen all the time, but sometimes we go for solution and we know that it shouldn't work in that way, but we force to use that direction or forsake publication sometimes. Maybe I'm wrong, but that's sometimes happening, and we try to see, does it make sense why we have to do that? And is it really visible for maybe in the end of the day to be beneficial or maybe commercialize it? I don't know, whatever direction you have to go. Maybe I'm wrong, but I don't know, how do you see this kind of, you really said something very important, and I don't know, why do you think we have this motivation sometimes to go something not make sense?
That's a good question. That's like a one that's really kind of heavily indicting academia in a way, in terms of, there's such a pressure for us to publish and to be innovating all the time, constantly, and that pressure to be constantly innovating oftentimes makes us okay, we got this to work once, so let's publish this thing, as opposed to taking a step back and spending the time that it takes to understand why it worked. How do I make sure it works every time? How do I make this thing really robust? And I think we all fall prey to that, because we have to, there's that pressure to put our research out there, especially in a hot field like soft robotics, where there's tons of people publishing all the time. It feels like all the ideas are in the air. And so I think there's a pressure that comes with that. I don't have a solution there, other than I tend to, if I see groups of people working on one set of problems, I tend to just kind of run the other way and work somewhere else where I feel like I have a little bit of time, because I'm a little bit slow with how I do science. But I think that to me is part of it, is just allowing yourself the freedom to ask questions, and ask different questions as you're trying to understand things. And I think talking about your work really helps too, whether that be teaching seminars, like short courses, any opportunity, group meetings, whatever, any opportunity you have to discuss your research with others. That's when you start to really know what you understand and what you don't understand. Because I think when you try to explain something to someone else, you can start to almost in your head see the holes in your argument, and it's kind of like, oh, I hope they don't ask that question, because I haven't thought of this yet. And I think that can be a really important tool for you to kind of check to make sure that the work you're doing, and that the model that you have, or the answer you have for why this works or when won't this work, I think that's a great tool for you to be able to kind of check and be confident. Because I think if you can explain your work to others, it in a clear way, where someone who's not an expert in your field can understand what you did and why it works, that to me is indicative that you truly understand it. And I think it's you see all of these discussions nowadays about papers that are hard to read and filled with jargon, and talks that are really high level and super advanced, and maybe a couple of people in the audience are able to get a lot out of it, but most aren't. To me, these are kind of failings of our ability to deeply understand something and communicate it to our peers. And that's what science, at least that's what it is to me. It's what it has always meant a lot, is partly the discovery and the understanding, but it's also that understanding is coupled with the ability to explain that to someone else. And I think, I don't know how to fix that culture, but I do think that that more of an emphasis should be put on scientific communication, broadly defined, because if for no other reason, it helps you do better science.
That's very excellent point. Thanks so much for being honest at that point. Yeah. So closing to the end, I have a few questions. First one, what's maybe your aspiration, or any other crazy ideas do you still have in your mind? And I don't know if you have any kind of ideas or aspiration when it comes to what you're trying to do in your lab.
Yeah, that's a really good question. I'm kind of constantly thinking about this, to the point where I think my colleagues are into it, where I'm constantly bugging them to say, what are the big questions in our field? Mechanics has been around for hundreds of years. Euler was studying bending beams in the 1700s. Like, there's the old expression, there's nothing new under the sun. Like, I mean, I work in a very dusty old discipline. And so I'm always concerned, like, hey, is there anything left for us to study, to explore? Are there big open questions that we can contribute to? I don't know if I have the answer. I have been getting really excited lately, thinking a lot about the way mechanics seems to matter in problems of morphogenesis and growth in biological organisms. That's been really, something that my lab has been thinking quite a lot about. I've been thinking a lot about some of the kind of open questions in soft matter physics, which are, I think the biggest questions in soft matter physics are still kind of around these ideas of understanding granular jamming and understanding, for instance, the crumpling of thin sheets. And so these are still areas that my lab is actively involved in, because, these are big questions that we are still searching for answers on. I think it's hard for me to project kind of like 10 years in the future, because what I end up happening is that we end up working on things and seeing connections between what we're playing with out of curiosity to the things that are happening around us. And that's what happened here. Like, we didn't set out to make a cool soft robotic gripper. We were just studying shape changes in thin materials that had cuts in them. Like, we had no kind of ambition to be roboticists, and we stumbled upon something that was clearly useful. And I really attribute that to the graduate student Yi Yang, who was the first author on this paper. He, we discovered this by accident, but he had the care and the critical eye to say, hey, that looks interesting. That's a mistake, but I should go and check out that mistake, because I think I could do something cool with it. I think that's how we've kind of often been doing experiments in my lab, where we have some kind of big picture questions that we aim towards, whether it be crumpling sheets or granular jamming problems. But along the way, we kind of allow ourselves to get excited and interested and curious about the things that emerge as we're studying these behaviors, which I don't know. I feel like it almost sounds like a cop-out, because I kind of don't have a grand vision of where all of this goes in the next 10 or 20 years. But at the same time, I think one of the most exciting things about studying soft matter physics is there's emergent behavior everywhere. And I kind of think that my lab science is kind of studying emergent problems that we encounter as we explore and try to understand more about the shapes of the objects around us.
That's interesting. Yeah, thank you for saying that as well. Yeah. So, do you believe ego is important for you when you try to discuss new ideas in the field in general? Do you think ego sometimes is important for you?
Yeah, that's a good question. I guess it a little bit so ego, I feel like, always has a negative connotation to it, but I tend to think of a kind of self-confidence and like in like a extremely naive way. Like, I want my students to think, sure, why can't I learn that? Like, I could probably figure that out. I could figure out, I don't know anything about robots. I can go and learn some things about robots. I kind of want to arm my students with that level of kind of self-confidence, where they can encounter a problem and not say, oh, that's outside of my discipline. I should focus on this because I do A, I shouldn't look at B. I want to encourage my students to say, oh wow, B looks really, really cool. I don't understand anything about that, but I'm going to go learn, and I probably can figure it out. And I was when I was starting as I was interviewing for graduate school at UMass Amherst, and I remember distinctly meeting with a professor and chatting, and he said, do you know what a PhD is? And I was, I don't know, what is a PhD? And he said, it's a couple letters after your name that says you can learn anything. Like you know, it might not be quick. You might not learn something really fast, but you know how to learn, and you know the path that you need to go on to learn something new. And it's just a document that says, yeah, I could probably learn that. And that's kind of the training I want to impart to my students. You know, like I did a PhD in polymer science. I don't do much polymer science anymore. And I want my students to be confident enough to say, that seems interesting. I want to understand that, or I want to explore that, or something about that is kind of magnetic for me. I want to study and learn, and I probably could figure it out, and I probably could make a contribution to that area. And that's probably ego, to be able to kind of say that, you know, to be able to say, yeah, I can learn that. Yeah, that's probably ego. But I hope it's more reframed as a confidence of, yeah, this is what I'm here for. I'm here to learn hard things. And if I came up with a cool idea and it's in a field that's not my field, like I know I'm confident in my ability to go and learn what I need to learn to be able to make a contribution there.
Well, that's inspiring. Yeah. And what could be the most important quality do you believe that you have to maintain? I don't know, what kind of quality do you believe that you have to maintain?
So if I have to pick one, I would probably say curiosity. I think that to me is like, if you're a curious individual, then you can get kind of excited by anything, or you at least have a sense of taste of oh, that's interesting. What is it about that draws me in? And so I think, to me, I think a lot about wanting to work with curious people. For me, I think more broadly, if I could think of multiple qualities, it's I think about curiosity, creativity, and like a critical eye. You know, like I want people who are going to create. I want, you know, we're scientists and engineers. I want us to be creating and making, and I want us to be curious about the world around us and how it works. But I think, you know, to be a scientist or an engineer doing high level research, you have to have that kind of critical sense about you, where you're self-critical about your own, you're going to be doubting what you're doing, to the point where if you're like, no, I triple check this is right, and then you can go on and say that with confidence to others. I think that critical eye of kind of taking care with your experiments or your simulations, and taking care with your mathematics. So those are the three that, you know, I'm usually looking for when I'm, you know, trying to find a graduate student to work with, is someone who's going to be curious, creative, and critical. And I think those three things together are the kind of the hallmarks of a good scholar.
Yeah. And there's any book inspired you, I don't know, maybe inside the field or outside, any book inspired you have ever read?
Say a book that inspired me?
Mm.
That's a good question. So I'm going to go completely off the reservation here, but this is a book that inspired me when I was really young. I was probably in high school or middle school or something like that. And I first encountered Stephen Hawking's A Brief History of Time. And I remember reading that book and just being like, my mind was opened into a world that just seemed simultaneously incredible, but also explainable. And I think there was something about that combination of like a wide-eyed look at all of this phenomena that seems just otherworldly, and it almost seems magical the first time you're learning about some of these things, but then to simultaneously have it be so carefully explained and easily digestible and readable, that to me, I think there's something to that, in which, you know, I was kind of drawn into the wonder of the world and the universe, but at the same time, kind of you're drawn in with that, but I was pulled in and kind of kept there by the ease at which he could explain these complex things, and the way that science could be made accessible to someone like me, who was just like a kid who was reading this and didn't know anything. And so that that had a big effect on me when I was younger.
Right. And I don't know if you have received any advice was life changing or stick to your mind any advices you have received and stick to?
I got some good advice when I was before I started as a professor, and it has stuck with me. And the advice was, don't do anything that doesn't matter.
Mm.
And I love that because you get to define what matters. So if for you what matters is raising a family and being a good spouse and being a good teacher, then do those things and do them well, because that's what matters, and try to brush off the things that don't. But I think it can be incredibly powerful, especially for young professors, people, either postdocs or junior faculty. The idea of like, you have a million things you can do, and there's just an immense amount of freedom of like, I could explore this, and I could write this paper, maybe I could write this book or this proposal, or I have to go teach this class. And I've always kept in the back of my mind of like, does this matter? Is this something that I'm going to be happy I did 10 years from now? Is this something I have to do because it's going to negatively or positively impact someone else if I do or don't? And so I often come back to, don't do anything that doesn't matter. And then I allow myself to kind of define what's going to matter to me and to my research group and to to all the things that I'm doing in life. And so I've always kind of stuck to that mantra of kind of trying to do things with intent and do things that are important to you.
That's very wise. I don't know if you have any final words you'd like to say to the audience listening to you. If you have any final words you'd like to say.
I guess the last thing I would want to say, and I think I kind of hinted at this during the discussion, but like, we made something that seems like it might be really useful, and I'm excited about that. But I think it's really important to emphasize that we didn't set out to do this. We did this because we were studying something really fundamental, and we kind of just serendipitously discovered something useful. And I just kind of want to, I feel like it's my job as someone who's studying fundamental physics and mechanics to say, hey, it's the ability for us to study these fundamental problems and fundamental questions that enables important innovations. And it's not as simple as, hey, sit down and make a cool robotic gripper. Sometimes you have to sit down and be playing with something totally unrelated, and then allow yourself to discover something. And so I guess the last thing I would say is that, we discovered this by accident by studying some fundamental mechanics. And I think we, as a community, but then even more broadly than that, should really never lose sight of the value of fundamental problems and studying kind of the fundamentals of disciplines, because that is what enables innovation.
Thanks so much, Bristol. I think that was very enjoyable and inspiring as well. I deeply appreciate your time. Thanks a lot. Thank you.
Absolutely. I was happy to be here. Thank you very much.